Yeah, thank you for the introduction. Also, thank you to the organizers to give me the opportunity here to present our work. So, I'm presenting continuous variable quantum computing on encrypted data, and this was done together with Kevin Marshall from University of Toronto and Christian Wiedbroek from CipherQ. These two guys did the theory behind this. And the experiment I will present was done by Christian Jakobsen, Clemens Schäfenmeier, myself, and Ulrich Andersen. IBM recently has announced and released a quantum computer in a cloud. So they have 5 qubits, superconducting, and they have a website where you can register, and you can perform computation on their quantum computer. I guess some of you have used this before, and this is, in my opinion, only the start. So with the further development of quantum computers, there will be more quantum computers in a cloud, and especially they will be in a cloud in the beginning because, well, right now you need these big cryostats, and you don't really want to have that at home. Might change at some point, but right now, this is how it is. So there will be a quantum computer for some select few in a cloud, and then you can, as a user, access it, book time, and use it. And this raises, of course, some security questions, as you send some information to this quantum computer. The quantum computer performs some operations on it and has the result. And actually, as a user, I don't want to have IBM my results. So how this can be solved, and the ideal would be, okay, I have an input to the quantum computer, it should be secret. My program could also be secret. IBM doesn't really have to know what I'm computing, actually. The output should be secret. And then some more practical things like I don't want to have too much communication between the servers, the quantum computer, and me as a client. And I don't want to have too much overhead, for example, in qubits. And so this is fully addressed in quantum fully homomorphic encryption. But the problem is that the overhead is very, very big. And so it is not really practical. And to reduce this a bit, there's the notion of blind quantum computing where you allow for more communication, but still your program is secret. And you need a lot of communication, and in fact what I'm presenting here is quantum computing on encrypted data. So we reduce the secrecy of the program, so we make the program public. But what we gain is that we have much less communication between the client and the server. It's still multi-round, but as you will see, this is not much, and it is only true for a certain subset of the gates. So this is how the scheme works. We have a client. The client encodes some information on a quantum state. It encrypts it by an encryption operation and then sends the quantum information via a quantum channel, a fiber, which is lossy, to the server who performs a gate or multiple gates and then sends the result back via the same quantum channel, and the client then can decrypt the state to get the final result. We are working with continuous variables. So the amplitude and phase quadratures. I denoted this as P, the phase quadrature, and Q, the amplitude quadrature. And what is shown here is a phase space representation, and the quantum states are then represented by Wigner functions. In our implementation, we used coherent states to encode quantum information, but the overall protocol is not necessarily restricted to that. And then, so we produce an input state, and then we want to encrypt it. And as encryption operation, we use displacements. And we do this randomly. So once we have an input state, we just add some other small or bigger displacement, which is chosen randomly. And say we want to use the same input state a couple of times, then we would choose this each time differently. So if you look at it more in a collective way, it would look like this. And so you smear out your state over the phase space, and you clearly see, okay, my initial input state is hidden. To quantify this encryption a little bit more, we measured the mutual information, as is shown here, between this big thermal state and the initial input state we chose, versus the size of the Gaussian distribution where the displacement operation for encryption is chosen of. And this is then shown here, and of course the mutual information goes down with higher encryption noise. Let me remind you what gates you have to implement in the continuous variable regime when you want to build a photonic quantum computer. And so it's actually universal if you can implement all of those. So it's displacement gates. That's basically the same as what we do in the encryption. U2, which I call here squeezing gate, because you need to have a squeezed light source for that. The cubic phase gate, which is a third order operation, that's a non-Gaussian operation. The Fourier gate and the controlled NOT gate. And these lower two and the upper two are all Gaussian states, so they are relatively simple to implement. But the U3 gate actually, as a non-Gaussian state, remains as a challenge, so this has not been implemented yet. So we encrypt our data with the displacements. The server performs a gate, and then when the result is sent back to the client, he has to perform a decryption operation, and that depends on the gate that is performed. So for the two displacement gates, we need just to undo directly the encryption operation. And for the squeezing gate, we also only need displacement. Looks a bit more complicated. Same is true for the Fourier gate and the controlled NOT gate. And the only gate where we need something else than a displacement to decrypt is the cubic phase gate. In the cubic phase gate, you need to do some displacement and also a U2 gate, so squeezing operation. And the squeezing operation in the U3 gate makes the implementation of the U3 gate itself a bit more complicated. And in fact, it has to look like this. And the reason for that is that the U2 gate doesn't slide through the Fourier gate. So what you have to do is you take your input state, this is psi here, you encrypt it, and you send it to the server. The server performs a U3 gate and a inverse Fourier gate. And then the client also needs to prepare a second mode. And he has to choose the value A randomly and perform a U2 gate and a displacement. Q prime is also chosen randomly on a momentum eigenstate. And then this is also sent to the server, who then performs a controlled NOT and measures one of the outputs. On the other mode, he performs a U2 gate with a certain parameter B, and the parameter B depends on A, but A is only known by the client, so the client has to send, classically, the value of B to the server. And when the computed state is sent back to the client, he needs to perform, before he decrypts, some additional displacements, and the displacements depend on this value M1 and on the value A. So first, the server has to communicate M1 back to the client, who can then perform the correction. And so for the U3 gate, we need another mode, and we need one more round of classical communication. So for these two values to send back and forth. So let me come to the experiment we did. to show that this is in fact possible. We implemented the U2 gate. In fact, we also implemented the displacement gates, but I'm restricting me here just to the U2 gate. And to make it a bit simpler, we decomposed the U2 gate into a phase shifting operation, a squeezing, and another phase shift. And we performed then just the squeezing operation instead of the full U2 gate, but it's basically equivalent. The experiment looks like this, that we took a continuous wave laser beam at 1064 nanometers. We added displacements with an amplitude and a phase modulator to produce an input state, and added to the same modulators encryption noise chosen from this huge variance to encrypt the state. We then sent this state to the server. We could add some additional loss, which is simulated by a beam splitter to simulate the quantum channel. The server itself was then performing the squeezing gate by injecting the input state into a squeezed light source. A squeezed light source is a parametric down conversion source made of PPK2P as nonlinear crystal, and it's a linear cavity here to enhance the interaction, and a 532 nanometer pump is used to produce the squeezed light. And then because it's a linear cavity, so if you want to inject directly a beam into this, you use a polarizing beam splitter and a Faraday rotator to get the back reflected light. I would like to mention here that this previous implementations of the U2 gate or the squeezing gate have usually used so-called offline squeezing. So what they did is they produced squeezing, vacuum squeezing, interfered it with the input mode, made a measurement on one of the outputs of the beam splitter, and fed this forward to the beam. And in contrast to that, we just directly injected the input into the squeezed light source, which potentially introduces more loss, but on the other hand doesn't limit in the amount of squeezing you can use. The beam then, after squeezing, is sent back also to the same channel, and then we had to perform a displacement to decrypt, and this is done by using the same encryption noise that is also only known by the client, and perform a phase shift and some gain, and then we just interfered this with an auxiliary beam here and at a highly asymmetric beam splitter to perform the displacements. To show what the protocol actually does, we performed homodyne detection after each stage and reconstructed the Wigner function. And here on this panel, you see the input state we chose, so a coherent state, and we then encrypted so that you get a huge plop. So please notice that here on the y and on the x-axis, the scaling is a little bit different to this one. Otherwise, you couldn't see this clearly. The server performed then a squeezing operation, which you can see, which you cannot really see here on the state, but it becomes much more clearer than after decryption that it is actually squeezed. To quantify how well this was performing, we did two different things that I want to present you. So first of all, we looked at the signal-to-noise ratio. So as signal, we used the input signal, the coherent excitation, and compared that to the noise. So if you use just the coherent state, it's a vacuum noise. And for the input state we chose, it's looking like this in the two orthogonal quadrature. So this is it's an arbitrary input state. And so after performing the squeezing operation, then if everything is ideal, the gate is ideal, you don't have loss in the channel, you don't add additional noise, then the signal-to-noise ratio should be preserved. And this is then here is shown with the dashed lines. If you perform the encryption, the signal to noise ratio goes down considerably, as it should. And this is then after the squeezing gate. And the interesting part is now what happens after when you receive it back. And this is shown in these two panels here. So for these two here, we encrypted the state, we computed it, we decrypted it. And to compare how well it works, we left out the encryption, but just worked on plain text. And this is shown here. So if you compare these two, the difference in signal-to-noise ratio, so this difference here, is due to the encryption operation and decryption operation. And in theory, this should be ideal, so the signal-to-noise ratio shouldn't be different. But of course, in an experiment, it's not perfect, so you lose a little bit. You lose a little bit more if you compare. So if you compare this, the step is actually quite big. And the reason for that is that we used 5 dB of loss in the channel, and also the gate itself introduced some loss. And this contributed then to this huge step here. So another way to show this is we compared the output state when we encrypted and when we didn't encrypt. So to show, and we have calculated the fidelity to show how good that works. And we did this actually for different encryption. And what you see is that in the red dots, there was no channel loss, and for the green dots, 5 dB of channel loss, so forth and back, 5 dB each. And the fidelity is, in fact, quite high. And it doesn't change much with the encryption, so there's no big additional penalty for using higher encryption. It looks a bit scattered. The reason for this is the inaccuracy in the tomography that we used to calculate this fidelity. It was a bit hard to put exact error bars on it, so it's a bit hard to say. And then you might notice that the red dots with no channel loss are usually a bit lower than the green. This is an effect of the fidelity. So if you add channel loss, all states go closer to the vacuum state, and then the fidelity rises automatically. So it's only half a good measure for that. So with this, I'd like to conclude. So I've shown you how quantum computing on encrypted data works with a continuous variable photonic quantum computer. The encryption operation is simple, you just need displacements. The decryption operation is also simple, except for the U3 gate, where you also, so for the others, you also only need displacements. And for all the Gaussian states, you don't need additional communication, and you only need that for the U3 gate. So if you want to build a universal quantum computer, you have to do that. The U3 gate needs extra squeezing, 1 round of classical communication, and you need to send 2 modes from the client to the server. A remaining challenge on the theory side is to formalize the security proof a bit more and deal with the effect that the encryption noise is not infinite. And so information can leak, as I have shown in the beginning. And with this, I'd like to thank you for the attention.
We have time for some questions.
Hi. Okay. So I'd just like to ask you to maybe expand a bit on that last point about the formalized security proof. So if you go back to the slide on the signal-to-noise ratio between the encrypted input and so do you have a sense of what that would correspond to, like in terms of trace distance between the encrypted input and a state that doesn't depend on the input?
Can you say that again?
Like so, like what this would correspond to in terms of if you look at the trace distance, let's say, between the encrypted input and a state that doesn't depend on the input at all, is what we would like to have, like for a formalized security proof.
I have no idea.
Okay.
Sorry for that.
Okay.
No.
Any more questions? Okay, let's thank Tobias and all the speakers again.